All right, everybody, I'm going to do a short lecture on an introduction into aldehydes and ketones. And one of the benefits of doing these short introductory video lectures on we're introducing some of the more simpler concepts so we can save some time in class for more practice and more complex analysis. And also, you have the option then in a video of doing it on faster speed to save yourself time if you don't mind me sounding like a chipmunk, or pausing the video when you need more time as opposed to in class. So it can both save you time and also give you more time as needed. So if you're wondering at all my rationale there. So we've had a slight introduction into aldehydes and ketones because of their relationship with alcohols. So some of this might feel a little bit review, which I think is a good sign. So to then start, I can handle this, right? Be on the right page. Aldehydes and ketones. Sorry. Aldehydes and ketones have a functional group that is called the carbonyl group. And you'll notice how close that Y is to an O. So it's the carbonyl carbon and the carbonyl carbon. I try to really say them carefully, but it's pretty easy to accidentally say the wrong one. And so that is the structural formula right there of that carbonyl group. And then here, make sure I'm pointing it, here we have it as a model. So you can see it's got the little trigonal planar structure. We have a carbon double bonded to an oxygen and then something on either side. And that carbon then there, just like we call the carbon attached to the hydroxyl group, it has a special name in an alcohol. This one would be the carbonyl carbon. And I want to emphasize that just because it allows us to then say the hydrogen off the carbonyl carbon. We know which carbon we're talking about because there could be a lot of them. Now, what's attached to these two sides is what makes the difference between the aldehyde and the ketone. An aldehyde has at least one hydrogen attached to the carbonyl carbon. So it's always going to have, the little H there at the end. There's a structural formula. A ketone has alkyl groups, carbons attached to either side. It does not have a hydrogen. And you're going to see a carbonyl carbon in chapter 14 as well with carboxylic acids. But for now, that double bonded carbon group, that carbonyl group, are aldehyde and ketones, and that's what's their functional group. Oh, there's our structural formula. So they look really similar, and the difference comes down to that hydrogen. And a memory tip that you can consider here for that is aldehyde here has that H. So the aldehyde is the one where the carbonyl carbon has at least one hydrogen off of it. The simplest of each, their common names are listed there, formaldehyde and acetone. So formaldehyde is the simplest because it has a hydrogen on either side. You can't get any simpler than one carbon and then the hydrogen on either side. This wouldn't be its IUPAC name, we'll talk about naming later, but because most of you would have heard of it as formaldehyde, it's good to be familiar with the simplest names, the common names of these simplest ones. And then acetone is the simplest ketone, also known as propanone, it's its IUPAC name. And you can see its formula there. This is where our acetate ion comes from that you learned about in 121. Very similar, except it's got a negative charge and lost a hydrogen, which is where the negative charge comes from. So physical properties. First of all, make a prediction. And pause the video and make a prediction on how you think the boiling point of aldehydes and ketones is going to compare to the other organic families we've learned about, such as alcohols and alkanes, and why. So pause for a minute, just like you would in class. Here's a graph that shows the different families that we've learned about. We have linear alkanes and ethers here at the bottom. We have our alcohols that we just learned about in chapter 12 up here, and then we have our aldehydes and ketones. And you can see there that they're kind of right in the middle of those two, and maybe that matched your prediction and maybe not. So why do we see that? Why do we have this midpoint? The carbonyl group is moderately polar. So this group right here, this carbon-oxygen bond, so it's moderately polar, not like as awesome as a hydroxyl group polar, but the electrons are being pulled up toward the oxygen, and so we have a slight negative here and a slight positive there. And more so than the ether, where we have the oxygen's electrons getting pulled to a carbon on one side and a carbon on the other. But we're not going to have hydrogen bonding between molecules because we don't have the hydrogen, that SNOF, as we say in 121. We don't have a hydrogen attached to the oxygen. So we're not going to have hydrogen bonding. Therefore, there's our little dipole arrows. The boiling point is going to be higher than just saturated and unsaturated hydrocarbons, which are fully nonpolar, and also ethers, which polarity is just really tiny. Because of that, the oxygen has the carbon on either side, so the electrons are kind of getting pulled back, but lower than our alcohols. And here's a diagram that kind of reinforces that. We do have an attraction between the particles. All molecules are going to experience some degree of intermolecular attraction. And we have those three classic types: hydrogen bonding, dipole-dipole, and London dispersion forces. Different compounds have maybe only one of those. And so that tends to be what determines boiling point, is those forces. So here we have the dipole-dipole attraction. The dipole here, this negative charge on our oxygen, is going to be attracted to the partial positive on our carbon. So they're all going to be attracted to each other, but it's not the strongest kind like we have with alcohols. So what about solubility? So again, pause and make a prediction based on what you know about water and what you know about polarity and what you know about solubility. So water can hydrogen bond with them. Now they don't hydrogen bond with each other. We don't have intermolecular hydrogen bonding, but we have a water molecule can bond with that polar group through hydrogen bonding. The hydrogen will be attracted here. Therefore, there's our therefore arrow. Smaller ones are going to be soluble in water. But just like with our alcohols and a lot of the ones we've looked at, if these R groups get particularly large, we're going to find they're not soluble in water. So the smaller ones for sure, as long as the R group doesn't have too much hydrophobic non-polar carbons in it. This table is just kind of comparing the different families in the ways we've already talked about, but it's good to review. Because it's easy to write a quiz question that's like, which of these is the most soluble? Which of these has the highest boiling points? And then be comparing across families. So we have an alkane up here. And the molecular weight is just to show that we're dealing with similarly sized ones. We have our aldehyde, our ketone, and our alcohol. And we see a steady increase in boiling point as those intermolecular forces go up. And then we have insoluble for our nonpolar alkane, and then these that have polarity, because if you have polarity, water can interact with you through hydrogen bonding. So the naming of aldehydes. So here's an example of one. I can tell it's an aldehyde because it has that H. You'll notice aldehydes are always going to be at the end. They're always terminal. That's because nothing can bond with this hydrogen on the other side. In our model kits, the little hydrogen only has one little hole in the sphere. That's because it will only bond once. And it's a really great reminder that then you can't put a stick in on the other side. So an aldehyde is always going to be at the end. So step one, we're going to name the longest carbon chain that contains the aldehyde group. And that's important. This has to be one of the carbons, and it has to contain that. The carbonyl group is carbon 1. So that means we don't actually have to locate it, because it's going to be like, no, this is carbon 1. This is the special group. This is the group that determines that this is an aldehyde, so it gets to be carbon 1. Then we're going to change the root of that hydrocarbon name. So this carbon down here has 1, 2, 3, 4 total carbons. So it would be, we're going to have butane, but we're going to drop the E and add an al. So butanal. Now this is difficult in the sense that we would name an alcohol butanol. So we have to be very careful with our writing. I need to see that's distinctly an A, not an O, but also even the way we say it. So you'll notice I tend to overemphasize butanal just to make sure. All the other branches and groups are named using what we've been doing all along. We're going to locate them, we're going to name them, we're going to give preference to certain ones over others, we're going to go with the lowest possible name possible. So we have then 3 bromobutanal. So 1, 2, 3, that's where our bromo is. But to tell us there's 4 carbons, and then al. Now one of the most common mistakes I see, and that I also regularly perform, is that I forget to include this carbon. This is carbon 1. So it's really easy to name this as a propanol, but this carbon is part of the chain as well. So here's another example, and I like this one, and you might want to pause the video for a second and try to name it yourself, because it's a good reminder of the naming the parent chain to include the carbon group, the carbonyl group. So here, when I look at this, I see 1, 2, 3, 4, 5. I see a pentane chain, but that chain doesn't include the aldehyde group. So 1, 2, 3, 4. So it is also a butanol with a substituted ethyl group off of it. Naming ketones is similar. Here we have one we could name. You could pause and even just make a prediction on how it would be named. You're going to find the longest chain that contains the carbonyl group. So it has to go through that carbonyl group. That carbon needs to be one of our carbons. We change the root of the alkane name, or alkene name, or whatever it would be, because it could name it as an alkene. Drop the E ending and change it to -one. Just like in the word acetone, even though that's not the IUPAC name, it's that -one tells us it's a ketone. I like that one because it's right there embedded in the name. Name the longest carbon chain. Oh, number, sorry, I can read. Number the longest carbon chain so that the carbonyl group has the lowest number. Now here we do need to locate, usually. And the reason is that in this chain, this carbon group could have been over here, it could have been in other places, unlike the aldehyde where it has to be at a terminal, it has to be at an end. And then name and number the other attached groups as before. So this one we're looking at then becomes 2-methyl-2-pentanone. So we have one, where they're even numbered for us. We have 5 carbons in our carbon chain. Off of the third group, we have a methyl group right there. And then we do locate which carbon our oxygen is double bonded to. One thing to keep in mind as you're drawing structural formulas is remember that since the carbon is double bonded to oxygen, it can only bond to 2 things on either side of it. So it's pretty easy to accidentally throw a hydrogen on here and give it 5. I see that a lot. So remember, carbon in general likes to have 4, bond in 4 ways or 4 times, and we're counting then this one is 2. So here's another example. So again, I'd encourage you to pause the video and try to solve it yourself. And the name here would be 2-methyl-cyclohexanone. That's a fun one. So we have 2-methyl, there's our second carbon is our methyl group. It's cyclic, it's 6, so cyclohex. And then we have a carbonyl group in our ring, so hexanone. Right? And then we didn't locate it because of the rules with our cyclic structure. And when we have a cyclic structure and we give carbon 1 becomes the group that makes it special. In this case, the carbonyl carbon is automatically carbon 1. Now, if I had more than 1, then I would have to include that. So some common names, and you don't, I do expect you, as you can tell in the blue sheet, to know the common name of the simplest ones and their uses, but just these 2 are probably the only ones. Well, I don't even know how familiar you would be with those, but like formaldehyde, its common name or its IUPAC name is methanol. And then some common names for ketones. I kind of like these names a little bit because they have that word ketone in them, so they tell you right away what family it is. So we have, methyl propyl ketone, ethyl pentyl ketone, and we just name the alkyl groups. Personally, I kind of like that naming system, but it's not an IUPAC one. Other examples. You don't need to have examples memorized. I just think it's good to kind of look at the structure and be like, if I didn't already know this was an aldehyde, would I be able to identify its common family? And then same for ketones. I think the cyclic ones throw me off, so be aware that you can have a cyclic ketone. Other examples that you've probably heard of before, we have our progesterone and testosterone. The "-one" in those names of those hormones tells you that we have a ketone. And we actually, you can see we have multiple ketones. carbonyl groups here in those hormones. So just wanted to, kind of put that plug in there for our biology. Here are some other fun examples. One, I just love this name, cinnamaldehyde. So you can see that a lot of spices and flavors that you might be familiar with come from not surprisingly organic chemistry, since we get them from organic things. And so we see those functional groups. We see the ketones and the aldehydes and the carboxylic acids then, right in our kitchen, right in our garden, right in our backyard. So here's a practice, and we're going to probably start right away on Monday with this. So you can, be ready to go or take a look at them. And if you have any questions or concerns, feel free to email me, or just be ready then with your questions when we do this right at Monday. Be like, I have my sticky note of questions from this lecture. So I'll see you guys soon, and I hope you have a great weekend.